Lecture 34, means of samples from normal populations. Recall from lecture 33, we have there the list of all the heights of women in the whole world right there at the beginning of that list, right? And we saw that those heights were normally distributed with mean 63.8 inches and standard deviation 2.6 inches. Okay, and I think I'm going to just draw over here what we ended up drawing. Maybe I'll draw it about right here. At the end last time, we had mu is 63.8, and we had our nice bell curve, came like that, and sigma is 2.6. Okay, so this is for women's heights, which are normally distributed, 63.8, comma 2.6. And yeah, going a little off the margin there, but that's okay. All right, now you might want to pause and read the next paragraph there. I'm just going to kind of zip through it, and what we're going to do here is what we did. How did we build that curve last time? We built the relative frequency histogram by reaching into the set of all of women's heights, that whole population of data, and seeing what a value was, and then plotting it. And putting it in the, whatever the class width was. I wasn't very specific about the class widths were or anything because I didn't want to go into too much detail. But the point was I kept grabbing data points out of that population and sticking them where they belonged in the relative frequency histogram and building that relative frequency histogram. And the result was, when we just did it essentially for the whole populations, we got this normal curve, right? Suppose instead of reaching in and taking a single woman's height, we reach in and randomly grab 10 heights and compute their mean, and then randomly grab 10 more and compute their mean. So what we're really doing is we're picking simple random samples of size 10. We're just grabbing those and computing the mean. So each time we do that, if we were just grabbing one, the random variable would be W. Correct? Because it's just randomly chosen from that normal population. But now we're grabbing 10, taking the mean, keeping track of what the value is, grabbing 10, taking the mean, keeping track of the value. We have these new set of values that are the means of the samples, right? Excuse me, sorry. So what I say here is we're generating a new population of data, the population consisting of the means of samples of size 10. So I just pretended to write another population down there of what you would get if you took a sample of size 10 and computed the mean. So the first one I got was 63.9 inches. Took another one, a sample of size 10, computed, and got 63.7 inches, et cetera, et cetera. So we have this new population of data. Question is, how does it relate to the old population of data? And how does it compare? And what I want to suggest to you is the following. I think that intuitively, what you would expect to see is that if you think of the mean of the whole population, originally it was 63.8 inches. If I'm grabbing 10, taking their mean or average, grabbing another 10, taking their average, et cetera, I get this new set of data. You might expect that set of data also to center right at the population mean, and that is, in fact, the case. It turns out this new data set, this new population, let's call it, because that's what it is, this new population has the same mean as the original. So in this case, 63.8, right? But what about the standard deviation? If I am randomly picking a single woman, it's going to happen occasionally. I'll get some woman who's unusually tall or unusually short. You expect that to happen once in a while. But if I pick 10 at random and take the mean, can you see that it's much less likely I'll get a mean, an average of the 10 that's really tall or really short? Because sure, in that 10 that I grabbed, I might get a tall person, but their tallness is probably going to be kind of smoothed out by the average or shortness of the rest of them, right? And I might get a tall and a short that cancel each other. Likewise, if I just get a really short person, all the others kind of will bring that are going to be probably more in the middle, they'll bring the average back more towards the middle. So what we should expect is that we probably should see all the data values that are generated by the random variable that come in this population. We should expect to see them clustered around the same mean, but probably less likely to be extreme. So they're going to be clustered a little bit more tightly. And when that happens, when you have a random variable values or data values that are clustered more tightly around the mean, you're talking about having a smaller standard deviation. And that's exactly what I have here. So I guess I'm getting a little ahead of myself. I'm going to say that in a minute, but I'll just say this. It turns out that the new population has the same mean. The values are clustered more tightly. About the mean. Okay, so now let me come over here then and draw that. So this is now going to be, I guess, let me just say, the next page says, suppose we were to build a relative frequency histogram and put all the data points that from our new data, from our new population in, what would we end up building? Well, I'm putting this right below here. This picture for you is on the other page, but I'm going to put it right below just so I can draw it in comparatively. What we are saying over here is that we expect to get the same mean, all right? But we should expect to see the data more clustered. So we should expect to see something maybe like this. This is much narrower here, and then it comes up and maybe goes like that and goes back down. So we still have a bell curve, but sigma should be smaller, right? It's more of the probability, more of the values that I get when I'm culling values from the population of means are going to be in closer here, right? So the greater weight of the probability should be in closer to the mean. And I guess I say below that if we think of W as the random variable that represents a randomly drawn number from the set of means, then W appears to be normal. So this right here, W bar. W bar is normal with mean 63.8, and well, right now, I'm running out of room, but I'm just going to say a smaller sigma. Don't know what it is, right? Smaller standard deviation, okay? And what I tell you here is that we're actually illustrating a very important fact. And now we'll just get down to the punchline here. Suppose X is a normally distributed random variable with mean mu and standard deviation sigma. So X is normal, mean mu, standard deviation sigma. Then I say, suppose we consider drawing simple random samples of size n. Here I'm talking about size 10, but just be a little more generic. I pick a certain n, and I'm pulling random samples of size n from this population and computing the mean each time. The resulting set of data gives me a new random variable, X bar, and it is normally distributed with the same mean. But here's the kicker. The standard deviation is smaller. By how much? You take the original standard deviation and you divide by the square root of the sample size. All right? There's some relatively deep theory that goes into showing that that's true, but it is true, and we're just going to accept it. This is a lot smaller because n is, some number, and when I, usually bigger than 1, if I'm getting a sample of size n, it could be, in this case, 10, or it could be 1,000, right? I take its square root, I get some number bigger than 1, sigma divided by that, this is smaller. So this does mean that the data should be more clustered. In fact, in our example, let's see, I guess I got room here. In our example, n equals 10. So what's W? W is right here, 63.8, 2.6, normally distributed. So W bar for mean is normally distributed with mean the same mean, comma, and then what will it be? It'll be 2.6, the original standard deviation, divided by the square root of the sample size, divided by the square root of 10. So what you get is normally distributed. It's 63.8 for the mean, and it works out to be 0.8 2, I'll go ahead and put another digit on there, 8, 2, 2, et cetera, like that, for the standard deviation. So the standard deviation is a lot smaller. The standard deviation here is 2.6, and down here it's less than 1, right? It's 0.822. So that's exactly what you expect to happen here. The probability has been pulled in and humped up, so to speak, and less of it is out on the tails because that standard deviation is smaller. All right.